We have an example problem here. We have a circuit. This picture comes from our textbook. Our question asks, what are the charge on and the potential difference across each capacitor in the figure? So we have 3 capacitors. We want to find Q and delta V for each capacitor. We know Q, C, and delta V are all related. Q is equal to C delta V for a capacitor. So going back to this process of following a path, if I start at the positive end of the battery and start just following the wires, I get to a junction, so I have a choice. I can either go through the 4 microfarad capacitor, or I can come the other way and go through the 12. If I continue following that, either way I get to another junction where then I must go through the 2 microfarad capacitor and get back to the other end of the battery. Okay. We cannot say that C1 and C3 are in series. C1 sorry, there's a lag here. C1 and C3 are not in series. If they were in series, we would be required, as we followed our path, to go through 4 and 2 and have no other choice. Likewise, we can also say C2 and C3 are not in series. Sorry, I'm waiting for my computer to catch up. And for the same reason, for C2 and C3 to be in series would mean, as I followed my path from one end of the battery to the next, I had to pass through both. There was no other option. Well, coming back to our picture, we could choose C1 or C2. And then we had to go through C3. So what we need to do is find an equivalent of C1 and C2. So we would still have our 9-volt battery, but we want an equivalent of the combination of C1 and 2. So I'm just going to call it C1, 2. This is an equivalent capacitance. We still have C3, which is 2 microfarads. Regardless of whether we choose to go through C1 or C2, we must go through C3. Okay, so C1 and C2, because we can choose either C1 or C2, that means these are connected in parallel. In parallel, we know C equivalent is C1 plus C2. We only have 2 of them in parallel, so we only need to add the 2 of them. The other thing we know about parallel connections is that delta V across those capacitors has to be the same. And it has to be the same as their equivalent. So this equivalent ends up with a capacitance. We simply need to add the 4 and the 12, so 16 microfarads. And then the 2 microfarads. So what this is telling me is we could have just put in one capacitor there that was 16 microfarads instead of having a 4 and a 12 in parallel. This still, though, I don't know the voltage or charge on these individually, so we will need to take one more step to find an equivalent of all three together. So the equivalent of adding these two in series. Okay, well, in series, our equivalent, which I'm calling C123, is 1 over C12 plus 1 over C3. So 1 over 16 plus 1 over 2. That's nice enough. They gave us a common denominator. So 1 over C123. Let's see. If we make that 16, we need 8. So 9/16. We still need to flip it, though, to get, C123. So C123 is our equivalent capacitance now that we're down to one capacitor. I'm going to leave it as the fraction because I can see that they are giving us a 9-volt battery, so things will cancel nicely. When we have one single capacitor connected to a battery, the potential difference across this capacitor will be the battery voltage, so the 9 volts. If I know the capacitance and the voltage, I can use our trusty little equation up here and find the charge. This represents the overall charge that had to move around in the circuit to reach equilibrium. So 16/9 microfarads times 9 volts, we have 16 microcoulombs is the overall charge that moved around to reach equilibrium. Working our way back, we want to go back to just the next step. So the step right before we got to the one capacitor. This C123 meant the equivalent capacitance of these two in series. In series, our capacitors have to have the same charge, and that charge is the same as the charge on their equivalent capacitance or equivalent capacitor. Okay, so we have capacitance and we have charge. So let's use this equation yet again, but to find delta V. Delta V is Q over C. So for the top capacitor, delta V will be the charge, the 16 microcoulombs, over the 16 microfarads, which that's nice of them to make that a beautiful 1 volt. Down here, same equation, but the values for this specific capacitor. 8 volts. Now notice as I follow a path through this circuit, 9 volts that the battery has. One of it is on the first capacitor, 1 volt. 8 volts is on the second one. 8 and 1 add up to be 9. That is a conservation rule that we will use many times. Okay, so this 2 microfarad capacitor, we can now say has 8 volts across it, and there are 16 microcoulombs of charge on it. So the charge and the potential difference. So we now have 1 out of the 3 completed. Coming back to this intermediate step, we do know the charge and voltage on this equivalent capacitor. This C12 represented the equivalent of C1 and C2 in parallel. In parallel, they have to have the same potential difference across them, and that is the same potential difference as their equivalent. So we can say, let me clean up my picture a little bit, that delta V is 1 volt for the 4 microfarad capacitor, and it is also 1 volt for the 12 microfarad capacitor. They're in parallel, they have the same voltage, and it's the same voltage that their equivalent capacitance has. Okay, well, charge is simply capacitance times voltage. So we're using the same equation over and over and over and over and over, 1 capacitor at a time. This time we have C and V, so 4 times 1 tells me I have a charge of 4 microcoulombs here. For C2, 12 times 1, I have 12 microcoulombs here. So a couple things to note. As we followed the path from one end of the battery to the other, we had our choice. Either way, though, we had to come back to this junction and then go through this 2 microfarad capacitor. When we think about charge and the fact that electrons are moving around trying to get to an equilibrium, here they've combined together on this 2 microfarad capacitor to be 16. Notice 4 microcoulombs plus 12 is our 16. This represents the conservation of charge. Whatever charge was flowing keeps flowing until that equilibrium is reached. The other rule we've been talking about is if 9 volts go in, as we follow a path, one path here, there's 1 volt for that capacitor, there's 8 volts for this capacitor. That gets us back to the battery. Well, 1 and 8 add up to be 9. That's a conservation rule as well. It relates to the conservation of energy, even though delta V isn't technically in and of itself energy. It's not energy in and of itself, but it's directly related to energy. The other loop we could take is to go up all the way over to the 12 microfarad and then down and back. Well, there's 1 here, 8 here, they add up to be 9. So it's really good to look for these conservation rules. One of them pertains to any one path or loop through the circuit, and that one relates to voltages, the potential differences. The other conservation rule is for charge. Whatever charge is flowing must keep moving or must have moved through the circuit to reach equilibrium.